around for another 2 weeks in the Jabal laboratory. So those of you who want can take advantage of this opportunity.
Okay.
Professor Uchida was for many years on the faculty at the University of Tokyo. He's still an emeritus professor there. He's visiting professor or guest scientist at some large number of other institutions. He's won all sorts of awards, including the Camerlionis Prize in 2006. The Camerlionis Prize is probably the preeminent prize in superconductivity research. I wanted to try to give an idea, for those of you who don't know him, of the role he's played in condensed matter physics and quantum materials. And I actually spent some time there. I've been part of all sorts of reports where people look at the state of condensed matter and materials research in this country. And I was trying to find some good quotes. And in the present context, I couldn't, because all of these reports say we need to spend more money on research because otherwise some other country is going to murder us. I didn't want to give credence to that, but what I want to tell you is that when any of these reports are talking about what we need in this country, they're thinking about Professor Uchida. Okay, so without anything else.
Okay. Can you hear me? Okay. Ted, can you hear me? Okay. Okay, good. It's my great pleasure to be here, particularly that this is the, I don't remember that how many times I visited Stanford, but I remember that the first visit to Stanford University in 1987, just 1 year, almost half a year after the discovery of high-density cuprate. Yeah, at the time I remember that all the buildings, particularly physics buildings, are very old at that time. But nowadays, I'm really surprised that all the buildings become renewed. So that when I visited this time, I completely lost my way to get to the physics department. Wow. Okay. Now, thank you very much for Steve for the very kind introduction. And it's my pleasure to... Okay. Okay. Okay, totally 3 microphones, okay. Okay. This is the subject I'm going to talk about. I frequently talked to many audience in this country and in other countries since 2006. I'll explain that why since 2006. That's because the TC, of course, in the stable material, the superconducting transition temperature stopped rising for more than 26 years this year. So that in that sense, okay, sorry. 2 big challenges for the high-density superconductivity physics, 2 grand challenges. One is, of course, mechanism of high-temperature superconductivity that had not been resolved yet. And second one, of course, because the TC stopped rising in 1993. So the 26 years silence in the TC rising. So that higher TC is another challenging problem that should be deserved to challenge for young generation as well. Okay? Of course, you may claim that these 2 challenges may not be dependent each other. But in reality, these 2 challenges are almost independent. When we know the mechanism of high superconductivity, that does not help us to rise the superconducting transition temperature. That is very old truth, because that, as you may know, that the BCS theory, that is very beautiful and great theory, but BCS theory can explain superconductivity phenomena, but never explain the TC values of the real materials. That is also the case, might be the case with the higher TC. When we get higher TC material, even higher than the cuprate, TC of cuprate, then is that helpful to resolve the mechanism? That's not necessarily true, but there may be some help to narrow down the many proposed theories, okay? So that today my talk is focused on the higher TC, go to higher TC. Okay, this is again I showed all the audience since 2006 here. This is the history of TC that is characterized by the quite long silence. Maybe 2006, just 30 years, since the highest TC, 130K, 35K, is realized 1993. 13 years is just the same as the silence between the niobium-3 germanium and high TC cuprate. In the history of high TC superconductivity, 13 years was the world record for the silence. Now, we are now in the high TC era, but in reality, in the stable, as far as the stable material concerned, we have another 13 years silence. That is very sad in the history. So that you may be pessimistic that TC might not go further away, all the way to the future, but we are not so pessimistic. I remember that in 1985, when Ted and Mark Beasley visited Tokyo, many people were pessimistic because this recorded value, 23K, looked at that time at the BCS limit. So that in terms of electron phonon mechanism, 23K is near almost upper bound. But now we are not so pessimistic because we know that TC should jump in some days. So that we are expecting that in some day near future, TC will jump up, hopefully to the room temperatures. Okay, that is the motivation of my talk. Okay, but for the metastable state, TC actually jumped up. You can see that cuprate 2014 jump up to 400K. But the lifetime of the superconductivity only a picosecond scale. And another one that may be famous for you, that showed up from the conventional electron phonon superconductor that incidentally happened at the same year, but the material applied by the very high pressure, TC went up to the almost near 300. I can show you some example. This is the element data. That is chemical composition and structure is known, H3S, which show that TC are almost 200 under the pressure of 150 GPa. And quite recently, lanthanum hydride, although structure is not known yet, but when applied near 200 GPa pressure, then these authors reported that TC is almost 260K. But you may feel that how high is this pressure scale? 200 GPa. That is quite huge pressure, well inside the Earth. Or in other words, if you imagine that 1 cubic centimeter solid, when you apply 200 GPa pressure, then the volume shrinks to almost 1/5. So that 200 GPa is so huge pressure, so that because the volume shrinks to only 20% at ambient pressure, so that everything will change under such a high pressure. So that in that sense, it's not surprising. But nevertheless, this is realized only under such a high pressure, so that we cannot put this superconductor to the ambient pressure, unfortunately. That is also the case with the picosecond superconductor. This is YBCO. When the YBCO material pumped by the laser pulse, then in the period of the few picoseconds, there appears some evidences for Josephson coupling between the kappa-oxygen layers that persist up to well over the 300 K. So that in that sense, this is room temperature superconductor, realized only in the picosecond duration. But this is not practically so important. Practically important, stable superconductor continues the its silence over 26 years. So that the one way to search for higher TC is that based upon these two distinctly high TC materials. One is copper oxide, cuprate. The other is the iron-based superconductors, which show that the highest TC 55 K at ambient pressure, of course. But unfortunately, even this iron-based material, TC stopped rising at the year just the discovery of this material, so that we still that 55 K is the record TC value for the iron-based superconductors. Okay. So the first way or first road to search for the higher TC is that what we learned from cuprate and iron-based superconductors, and based upon that, what we have learned from both systems, there might be some guiding principle to search for the other, maybe third family of the following copper and iron. This is the first part of my talk. Okay, let's play with something about periodic table. We are thinking by looking at this periodic table that why copper and iron are so special. You can see immediately that element copper is located one block left to the zinc, and iron located one block right to the manganese. Then why zinc and manganese is so special is that it's the electron filling of the 3D orbitals. Zinc, specifically zinc 2+ ionic state, all the 5 3D levels are doubly occupied, so that perfectly filled in this zinc station, so that when we move to the copper, then one orbital is vacant, so that one electron is isolated on that orbital. The similar thing that happens. The manganese is particularly manganese 2+ state, is just that all the 5D orbitals, 3D orbitals are singly occupied. That is a very special situation of electron configuration. Then iron, one electron add, so that violates this special filling. That is one lesson we learned from why iron and copper are so special. That is just the next element to the special electron filling configuration. Okay, as a consequence of that, you can see that in other than that special filling, there are many commonalities between iron and cuprate. Both systems basically show the square lattice structure, and copper, 3D transmetal copper and iron are strongly bonded with the neighboring anions. In the case of cuprate, oxygen, and arsenic or selenium in the case of iron-based one. This is the structural commonality, but I would like to stress that the very strong covalent bonding between anion and cation is another important commonality. And also, I already said to you that in this configuration, there is some vacant or singly occupied state. In this cuprate case, dx square minus y square orbitals are singly occupied. In the case of iron 2+, 2 orbitals are singly occupied. That of course, this isolated electron has a localized spin, so that starting material is always antiferromagnetic, so that we need doping to get superconductivity. That is also the case. Electron doping, either electron doping or hole doping are possible in both cuprate and iron-based materials. And also for the advanced issue is that these superconductivity has a quite unconventional pairing symmetry. In the cuprate, many people well know that the pairing is D-wave symmetry, which can be expressed that the momentum-dependent superconducting energy gap. That is cosine kx minus cosine ky. That is well known. In the same context, iron-based material, basically S-wave, but it's S plus minus wave. S plus minus means that the superconducting order parameter changes sign between two different Fermi surfaces. So that if we use some convention that unit cell contains 2 iron atoms, then the order parameter of S plus minus wave pairing can be expressed cosine kx plus cosine ky. You can see that only that the sign changes. In that sense, iron-based superconductors and the cuprate say that both sides of the one coin. So that these are really similarity between the two systems. So that this is the starting point to search for the third family of high-tissue materials. These are summarized of genes of unconventional high-tissue superconductors. One is, of course, electronic correlation, because it's derived from 3D electrons. And some orbitals should be singly occupied. And second one, basic playing ground is a two-dimensional square lattice. And in that, strong cation-anion bonding exists. Third, because of the isolated d orbital, antiferromagnetic interaction is very strong, because kappa-kappa magnetic interaction or iron-iron magnetic interaction takes place through some anions. We call this a super exchange coupling. It is well known that in the case of cuprate, this super exchange coupling is very large as compared with other magnetic material. And many people believe that this large energy scale should be responsible to the high TC in the cuprate. That might be also the case with iron-based one. Okay, then this is the main subject. Where the third way or third element we should look for. Okay, from the lesson that the copper located next to zinc, iron located next to manganese, there is the other neighbor, that is chromium. Chromium is the one orbital of the chromium 2 plus state, of course. One orbital is totally empty. But many people so far believe that chromium, as well as manganese, are very stable in the magnetic state because it possesses very high spin quantum number state. But that is not the case. Quite recently, chromium arsenide was found to be superconducting at very low temperature, Tc only 6K. But the surprising thing is that this compound, chromium arsenide, is a 1D material, almost linear chain material. And usually the linear chain material becomes superconducting by applying high pressure. But surprisingly, this material is superconducting without applying pressure. So that chromium is one of the possible candidates for the third family. Next one. Next one, now we have seen that fully occupied zinc and half occupied manganese. Then there's the third one, that is totally empty situation. That is realized in either titanium 4 plus, titanium 3 plus, titanium 4 plus or vanadium 5 plus. In this case, that d orbital are totally empty. Then this is the third special occupation configuration. Then we should go to the right. Of course, in this case, there is no left. Right, one block right means that 3D1 configuration. That is realized actually in many materials, titanium compound and vanadium compound. So that I like to propose that this is the, another third family. Yeah, actually, very old known material, titanium oxide, that has a spinel structure, shows surprisingly high Tc values. That was almost 40 years ago or 50 years ago. But apparently, oxide is not a suitable counterpart or partner of titanium or vanadium, because that we cannot expect that very strong covalent bonding or very strong superexchange coupling in the case of titanium oxide or vanadium oxide. So we have to look for this more suitable partner other than the oxygen. Okay, this is the first route I would like to propose you. Second one is of course already known cuprate. Because the cuprate is very exclusively shows high Tc. Actual Tc values are far exceeding liquid nitrogen temperature. So that one of the realistic way to search for higher Tc is to enhance Tc of the non-cuprate. I say that it's conventional cuprate. But actually, since 2006, I mentioned before, I have been trying to enhance the Tc of the cuprate, conventional cuprate, but never been successful. That is so difficult to exceed 135K realized in 1993. I have thinking that various ways to enhance to TC of cuprate. One way is to control disorder. As you may know that the cuprate basically disordered, realized disordered crystals. So that if we can reduce disorder as much as possible, we expect that TC goes up. Yeah, but unfortunately, there are some results. For example, you may know that bismuth-based cuprate. That's normally 90K superconductors. In this case, by reducing disorder in the bismuth-based cuprate, I could increase TC from 90 to 98. But the 98 is far below the world record of the mercury-based cuprate. And also, second one, many people know that the factor, one of the important factors that influences the TC value of the cuprate is the apical oxygen distance from the copper plane. Many people believe that longer apical oxygen distance is better for the higher TC. But we did not, unfortunately, know how to increase the apical oxygen distances by controlling some element, by combination of element. But so this is no effective way in real material. And third one, that is quite effective in enhancing TC, is to make a package of the many copper oxygen layers. We call this a multi-layer effect. Okay, this is a typical example of the multi-layers. This is mercury-based one, which showed world record TC value for this particular case. This is a package of 3 copper oxygen plane that recorded TC 135K. But there is other packages, 1, 2, 4, 5, even more. And we knew that the TC actually goes up when the number of copper oxygen layers increases. 1 layer, single layer, double layer, 3 layers. But unfortunately, that for exceeding the 3 layers, there is some level off of the increase of TC. And when we go to the 4, then TC unfortunately decreases. Okay? The reason why is that the charge imbalance, namely that the whole density of the copper oxygen layers are different between outer copper oxygen plane and the inner copper oxygen plane. You can see this is the estimate from the photo emission measurement as well as the NMR estimate. You can see that in the outer copper oxygen layers, there is a tendency to be overdoped. Whole density of almost 24%. But on the other hand, in the inner layer, the whole density tends to decrease remarkably. Why does it happen? It's very understandable by the chemical consideration. You can see that inner layer normally sandwiched by calcium ions on both sides. Because calcium ions is 2+ charged. So that if the copper oxygen plane is sandwiched by 2+ calcium layers, then to maintain the charge neutrality, copper oxygen layer should be more negatively charged. That prevents the whole, to increase the whole density in the inner plane. Okay, that might be the main reason why TC go down when the number of layers exceeds 4. And that happened also, already happened in the n equals 3 layers. So that, of course, the practical way is to increase or decrease this charge imbalance. But unfortunately, I could not find any way to improve the imbalance of the charge density between inner layer and outer layers, so that the result is not so dramatic in this load. So I have been looking for the third load to the higher TC. That is for the conventional cuprate, we do not expect no dramatic increase of TC. But if we can find other type of cuprate, then we may have a hope to increase TC. This is the main topics I'm going to talk in this colloquium. Okay, of course, Ted Gibo also proposes the third load. This is Ted Gibo load. He focusing on the very high hole doping region, where he expected there should be a second TC dome. And the existence of two domes is very popular in the ion-based superconductors. And in the case of ion-based ones, second dome has always higher TC. So the TED load is quite a reasonable way to search for high TC. So that he proposed one material. And of course, he also proposing another material that is related to our materials. What I'm going to introduce you that, showing you that there appear to be quite a new type of cuprate that has chemical formula, something like this one. This is very simple. The material composed of only three elements: barium, copper, and oxygen. Basically, the structure looks quite similar to the first Bednorz-Muller cuprate. It's basically 214 structure, but you may notice there are some differences. That in the case of Bednorz-Muller material, apical oxygen distance is elongated. On the other hand, this compound, new cuprate, has a very compressed octahedron. And more surprising fact, this cuprate, there are a lot of oxygen vacancies. In the conventional cuprate, oxygen vacancy should exist out of the kappa oxygen plane. But in this new cuprate, kappa oxygen plane is highly oxygen vacant. That is quite crazy in view of the conventional cuprate. But nevertheless, this is true, evidenced by neutron diffraction experiment. You can see that almost 40% of in-plane oxygen sites are vacant. That is very crazy cuprate. Another characteristics, this is oxygen vacant kappa oxygen plane, and apical oxygen distance is very short. And also, this is highly hole doped. In that sense that it's shared with the Ted Gibo load, highly hole doped cuprate. You may remember that these three characteristics are quite opposite to the, many people thought that the optimal conditions of conventional high-density cuprate. One is perfect kappa oxygen plane. Second is elongated apical oxygen distance. And third one is a relatively small hole density. That is quite distinct cuprate in this sense. Okay. Although the TC at the moment is only 73 K, But it should be compared with the almost nearly isostructure lanthanum 214. In the case of lanthanum 214, TC only has 40K. It's almost a factor of 2 higher in this simple chemical formula compound. Okay, skip on. But we are still hoping, or there is some evidences for we can expect a much higher TC. That is the strontium counterpart. Strontium 2 kappa O3 plus delta. That had long been known since 1993 again. That actually that the TC, highest TC realized in this strontium 214 material is 98K. This is the highest TC among the known high TC, single layer high TC cuprate. But unfortunately, this material is not suitable for the further studying because the superconducting volume fraction is always small, so that we cannot identify which phases, which structure is responsible for the superconductors. So that, but on the other hand, barium-214 is very good material, which shows bulk superconductivity. Superconducting volume fraction almost near 100%. And from the structure analysis, it's a single phase material. This material, this is in the following. My talk is my own speculation based upon this oxygen deficient structure. Here, okay. Okay. I want to talk about you that why this oxygen deficient cuprate is so important for higher TC is that one is we can expect a larger superexchange coupling constant between neighboring kappa spins. You can see that this fact. In the case of conventional cuprate, spin just align antiferromagnetically in the square lattice. So the superexchange constant, superexchange coupling is very huge as compared to other magnetic material. It's 1,500K. But we know in other cuprate, specifically the chain cuprate, the superexchange coupling constant becomes much higher than two-dimensional cuprate. Incidentally, these 3 experiments almost independently reported in 1996. These values are significantly larger than the superexchange coupling constant in two-dimensional cuprate. So that what we expect from the oxygen deficient kappa oxygen plane is that you can see that there is some void or vacancies in the oxygen site that just disrupt kappa spin and kappa spin superexchange channels. So that, okay, I forgot to say that. Why two-dimensional cuprate show the smaller J superexchange coupling constant is that a little bit advanced knowledge of the spin-spin interaction. That there is 4 cyclic spin interactions actually in the square lattices that reduce it, that the magnitude of the direct superexchange coupling constant J. But this type of 4 cyclic spin superexchange does not exist for linear chain material. That is the main reason why the J for linear chain is so large as compared with the two-dimensional cuprate. Okay. Particularly important that now we have an oxygen deficient kappa oxygen plane. That in many places, such a super exchange coupling is disrupted, then there is no contribution basically for this full cyclic spin contribution that is negative to the actual super exchange coupling constant. So that we expect that in this oxygen deficient oxygen plane, we expect larger magnetic coupling, but in many models, that larger J might be favorable for higher TC. This is one thing why the oxygen deficient oxygen plane is so important for higher TC. Okay, let's move to the second, multilayer. We are now imagining multilayer structure composed of the oxygen deficient oxygen plane. That is very good, as I will show you immediately. You can see that this is a proposed three-layer structure of the oxygen deficient oxygen plane. You can see that this is the oxygen deficient oxygen plane, outer plane, two outer planes, and one inner plane. If you look at the environment surrounding the oxygen plane, you can see that this vanadium oxygen layer is basically electroneutral. Again, electroneutral vanadium oxygen layer, these are sequences. You can see that there is no difference, basically, between outer layer and the inner layer for the environment, electrostatic environment of the oxygen plane. So that no possibility to stop TC rise or reduce TC for the multilayers we have encountered for the conventional cuprate. So this is the my own proposed compound, which we expect the higher TC, higher than 135 K, realized for three-layer mercury-based cuprate compound. Okay, this is not so unrealistic, I should say. Already in earlier days, there is some possibility for the multilayer structure for the strontium counterpart. Actually, these authors proposed some multilayer structure, but at that time, no one knows that this cuprate has oxygen deficient oxygen plane, but they proposed the structure of this multilayer structure. This is so-called Dadderson Popper type multilayer, which has showed a quite equivalent inner plane and outer plane situation. Okay, I'm a little bit tired, so let me finish by showing this slide. So what I expect, and probably everyone would agree, that we can realize a jump as we experienced in 1986, another jump of the TC values someday in the near future. Thank you very much for your attention.
Are there questions?
Yeah. How much money do you need?
Probably money is not so important factor to realize higher TC, because the manpower is most important.
You know what I'm asking.
Yeah.
You need a budget, and you need to train people.
Okay.
It takes a lot of time.
Yeah.
So, what do we need?
I retired 6 years ago, so I am not interested in any budget now. I'm sorry.
Okay.
Yes.
How technically coupled are HC and TC, and are there any interesting discrepancies?
For the new cuprate, you ask? Okay, yeah. Yeah, unfortunately that we are now only have a very preliminary data. But anyway, that for this particular compound, HC2 value we estimated is 80 Tesla or something. It's fairly large. Okay.
So I have a question.
Okay, sure.
So you mentioned the photo-induced enhancement
Okay, yeah.
superconductivity, which I guess is certainly intriguing. Does that give you any suggestions on where to look? So, I mean, superconductivity for 1 picosecond is presumably not very useful.
Yeah, good.
But does one have any insight into what's being changed that's producing?
Okay, unfortunately, no one knows that the exact mechanism why in this short period that the situation almost as room temperature superconductivity realized. One initial thinking is that because of this pumping probe is just at 20 terahertz, that corresponds to the 80 millielectron volt energy. That corresponds to that eigenfrequency of the actual oxygen vibration. So that in the initial stage of this study, that these people propose that actual oxygen distance gets longer, which is suitable for high TC at the time. But now they never propose such a scenario. I don't know that the current situation of the. Steve, do you have any idea?
Several, which maybe is equivalent.
Okay. Yeah.
May I ask another question?
Yeah.
So can I ask another question, or other people are more important?
You're more important.
Okay.
Okay, I'm more important.
Okay.
Over the years, I worried myself
Okay.
that what might be special about copper was just how it grows. And that when the particular crystal structures are very rigid.
Right.
And I kind of worried about that. So do you have an opinion about that? Is there a possibility that what happened in the cuprates is a structure thing? That just because of the way it grows,
Yeah.
that it's the particular lattice is what's doing it.
Okay.
But there are other things that grow with the same structure.
Yeah, yeah.
Okay. I should say that
Yeah.
under ambient condition for crystal growth, copper oxygen CO2 plane is very stable, so that it's quite robust for ordinary synthesis route. But this new cuprate are synthesized only under very high pressure, 18 GPa, say. In that case, I thought that such an oxygen deficient structure is possible. But unfortunately, different from 200 GPa material, we can just get such a high pressure metastable structure even at ambient pressure. Because 18 GPa is not so large as compared with the 200 GPa.
Yeah.
I have given the right, correct answer to you?
No, you know more than I do.
Okay. Wow.
So we were at the meeting on Friday, so we recently found that cuprate, it's unique in that when we put it into a magnetic field, it orients orthogonally to all the rest of the
Yeah.
on the C-axis.
Yeah.
So it picks out a unique axis we're calling A. Does that make sense in the context of your spin orientations along the chains and things like that? Or does it show that strontium cuprate differs fundamentally from the barium structure?
Okay. Yeah, that's a very interesting question. But at the moment, I have no idea about the orientation of spin in the Kappa-oxygen plane, unfortunately. But as far as I know, that in conventional cuprate, spin tend to be aligned along the Kappa-oxygen plane. Is it true?
No, they all line up.
Aligned perpendicular?
They all line up in
Okay.
the C direction.
Yeah, but depend upon probably materials, cuprate materials. But I don't know that which spin orientation is good for higher TC. Okay.
Okay, maybe one more question.
Today, when you've got a new candidate,
Yeah.
you have to test it empirically, and in the future, do you see an opportunity to be able to simulate more?
Computers.
Computer
Is
to
it possible to use more powerful computing to simulate candidates in the future?
Okay, unfortunately, I don't think so, because as far as we know, almost 99 or over 99% of the superconducting material could not be predicted by some theoretical or computer calculations. That might be okay. I'm not so optimistic for the computer simulation.
All right, let's
Thank you.
thank Professor.